still got 16 participants. That means either most of you are asleep or some of you are still awake. I am going to move on to the main topic. I've got an hour. If this is going to be a WEA members talk, I have to bring it in at about 45 to 50 minutes. So I'm going to get cracking and hope I don't overrun. Otherwise, I'm going to end up stripping bits of this talk out. Okay, so I'm trying to restore back to my browser. This episode, in this bit, little introduction, we're going to talk about how to find life on other worlds. So we're going to try and make some headway. Now, as I said, those of you who have done my normal class will find this eminently familiar. If you want to sort of go away and have a cup of tea, I don't really mind, but you will find this familiar. But anyway, so this section is all about the search for life on other worlds, the search for exoplanets, the search for life as we know it, to discover if we are the only things in the universe, the only intelligent life in the universe. So we're going to have this little introduction, this preamble. We're going to look at what's an exoplanet and how do we find them, the particular techniques that we use. Now, I have fully revised and reworked a lot of the graphics for this section. A lot of the theory is bang up to date as well. And we're going to ask the question, well, hold on a minute. If we're getting so good at detecting stars, if we're detecting planets around distant stars, if we're getting good at sniffing out where ET might be lurking, if we're looking for the signs, the telltale signs of ET, why aren't we seeing them? Where are they? Where have they gone? And we're going to ask the question is, maybe we've already found ET, we just don't know it. We've not spotted the telltale signs. And then we're going to finish by looking at a conference that took place very, very recently, fronted by NASA. It was talked about astronomy. I got the information from Astronomy Picture of the Day, which is a very, very good website. Check it out. Just Google Astronomy Picture of the Day. It's absolutely fascinating. And a conference that took place very recently about when are we going to find intelligent life out in the universe? Can we set some kind of intelligent timescale as when we might actually stumble across some form of life? And the results, the findings were absolutely astonishing. We may be on the cusp of completely reevaluating our position in the universe. And I don't say that particularly lightly. So here goes. I'm going to have a question and answer session, 10 minutes, if there's time. But I've been told to be off here at about 9 o'clock, so can't stick around for too long. Anyway. Big question, big ticket question in astronomy these days is there anybody out there? An awful lot of time and effort and money is going into answering this question. It's a big philosophical question. We don't have any good answers to it. It's like other big philosophical questions. Usually, where are my spectacles? Because I spend most of my working day looking for my glasses. And what happened to my other sock? That's another one that cropped up this morning. The other question, is there anybody else out there? We're trying to be serious now. Are we genuinely alone in the universe? And what happens if we really are all alone in the universe? Isn't it slightly frightening that we are the first species to emerge to achieve sentience? And why hasn't anybody else done it? And if they haven't done it, why haven't they done it? Is this something ahead of us, that's going to stop us developing any further? We don't know that. Extraterrestrial intelligence, the idea of ET is core to our culture, certainly in Europe and North America. I'm not sure about other cultures, certainly Japan, very into this idea that we are being visited by extraterrestrials who are older and wiser, and they have better technology and bigger ray guns than we do. If we're looking at science fiction, we think about aliens. If there weren't any aliens out there, Captain Kirk's 5-year mission would have been a lot shorter, saved an awful lot of money on toupees. Will Robinson would be completely lost without his robot, and people would be asking who this Doctor Who bloke is. Let's try to be fairly flippant, I guess, but it's a serious question. Where would we be without aliens? Maybe it's really hard for us to accept that we might be the only intelligent life in the universe. And, sitting back, have a think about that. How would you feel if we really were the only ones? We're the spearhead. We're the ones that are supposed to be setting an example to every other species out there. How do we survive. It's that simple. How do we keep going? How do we avoid blowing ourselves up? So this session tonight is about the search for life on other worlds. More correctly, life like us. Humans, human life, like similar to us. Many different variations, all essentially the same under the hood. So that's what we're looking for. We're looking for life, but there are other forms of life that we find. Now, this is a set of images I found during the week and left me absolutely flabbergasted. This is a real creature. If you can see it moving, it's a real puzzle. It lives in the Black Sea. It's called a Black Sea angel. I have never seen anything like this before. That's absolutely stunning. There's no CGI or fake imagery here. That's absolutely stunning. How did this thing escape my attention for so long? And if we're going to start looking at what life is like on other planets, you just have to look at the diversity and extremes of life on this planet to be able to come up with some kind of an idea. So where are we in the universe? This is me in the northeast of England, as you can probably tell from my sweet dulcet tones, as I managed to just tie my headphones around my leg. Here we are. This is a picture of our solar system. An overview. Notice that the size of the planets is roughly to scale. The distance is not. Otherwise, it would be very hot and crispy. But it gives you an idea of the structure of our solar system. So if we're going to find life out there, we're going to expect to find rocky planets close to the sun, close to the host star, and gas giants further out. And that's just if we're just being familiar with our own solar system. So that's the sort of thing we're going to look at. However, the problem is detecting planets around distant stars. If you look at this photograph, there's a genuine photograph. It's been enhanced by a computer. It was taken by the Cassini space probe, not far from the planet Saturn. It was taken about 10 years ago, something of that order. And that little blue dot, roughly in the center of your screen, that's us. That's all we can see of us. As soon as we start to move out into our solar system, the small size of Earth becomes readily apparent. We are very, very small. We don't reflect much of the sun's light into space. As soon as we get any distance away, we pretty much disappear into the background. And the same is true of planets around distant stars. Finding other planets isn't easy. For a start, they are very, very distant, and like some people, they are extremely dim. They don't give off any light of their own, they reflect the light of the host star, so we have to somehow knock out the light from that host star to stand a chance of seeing them. So the term we're going to use is exoplanet. That is a planet around a distant star. That is to differentiate it from the planets that we have in our own solar system. So the term we're going to use for a planet around a distant star is an exoplanet. How do we go about searching for planets around distant stars, given that they are so far away and given that they give off so little light? The first question that we have to ask is, how far away are the stars? Well, and you thought it was a long way down to the paper shop, to paraphrase Douglas Adams. The first person to really tackle this problem to any great degree, there's some evidence, I have to contradict myself here, there's some evidence that the Greeks made an attempt to figure out how far away the stars were. The Greeks passed on their information, one form or another, to the Islamic astronomers, who made similar attempts to discover the distance to the stars. There's some evidence that suggests that the Chinese tried to measure as well. Chinese astronomers about 2,000, 3,000 years ago, they also failed. The first person in European culture that we know of to really have a go at figuring out the distance to the stars was Sir James Bradley. Now, he was a London-based astronomer, active about 60 or 1710, something of that order. And he started to investigate this principle, this technique called stellar parallax. Now, if you want to know what stellar parallax is, simply hold your finger at arm's length and close one eye and open the other, then swap eyes. You will notice how the thumb at the end of your hand shifts position. Except in Bradley's case, he wasn't talking about the length of your arm, he was talking about the Earth's orbit. So Bradley's theory was that if you measured the position of a star overhead with respect to the background stars, So if you know roughly the size of the Earth's orbit as well, make a rough guesstimate about the size of the Earth's orbit, and you measure the angle to the star called the zenith star over your head, because it's directly over his head in London, and if you measure its position with respect to the background stars, you should be able to see a change from one extreme of the Earth's orbit to the other. So he would measure the position of the zenith star with respect to the background stars in January. He would wait until the Earth was on the other side of the sun the following July, 6 months, 7 months later, and he would repeat the experiment. So that he would measure the zenith star and the angular distance to the background stars and see if there was any change. And his theory was that if the stars were relatively nearby, you should be able to detect a change in the position of the background stars, the foreground star with respect to the background stars. So that's exactly what Bradley did. He recorded the position of a bunch of stars with respect to the background stars and tried to see if there was any difference. Now, he did this first set of measurements in January. He repeated them in July and came to the conclusion that there was no change. He couldn't detect any real change. His conclusion was that the stars were very, very distant indeed. He had real trouble noticing any kind of difference whatsoever within the limits of experimental error. So he concluded that the stars were very, very distant. It was left to this guy, Friedrich Wilhelm Bessel, German astronomer, active a little bit later on. Now, by the time that Bessel was observing the night sky, telescope technology and the quality of optics, the build of telescopes, the precision with which we could measure the position of stars had gone up considerably. It's certainly easier to make very accurate measurements of stars in the sky. And Bessel was able to make a measurement of one particular bunch of stars, and he came to the conclusion that there was one star in Draco about 9.8 light years away. And that was a phenomenal distance. That really boggled his mind. And he spent a lot of time debating over whether or not he should publish this information because he simply didn't believe his own results. He took a great deal of time and trouble to check and recheck his estimates. And that distance of about 9.8 light years stands up very, very well against modern values. And he did. You thought it was a long way down the paper shop. So even some of the closest stars are a very long way away from us. For instance, light takes, well, 1 light year to travel that distance. 1 light year is a unit of measure. That's how far light travels in a year. The nearest star to us, Alpha Centauri, is about 4.3 light years. What that means is that if a beam of light left Alpha Centauri, it would take 4.3 years to reach us here on Earth, which is really quite staggering, the distance involved. Bear in mind that it takes light 8.5 minutes to get from the sun to the Earth on average. So you can guess the distance to the nearest star is very high indeed. So we now know that stars are a long, long way away, and consequently, so are the planets in order about them. So that means that they present a very, very small object to view in a telescope. So obviously, with a standard telescope, normal telescope, even some quite big telescopes, you're going to have a real job actually trying to image a planet around a distant star. So we have to use another technique. We have to use a series of indirect measurements to figure out how far away these planets are, and if we're going to detect some of these planets at all. Now, we get a clue as to how we do this if we study the motion of our own sun. So this animation shows the position of the sun in space. You will notice that our sun wobbles. Now, this is vastly speeded up indeed, over a period of many years. And what's causing the sun to move away? You see, the sun is at the center of our solar system, as we were taught in school. It's Nicholas Copernicus. It spins around a common center of gravity called the barometric. Yeah, I'll try and, probably got the wrong word. Barycentric, the barycenter. I'll try and get that right, of the actual solar system, a common center of gravity. And it's pulled out of position by some of the bigger planets. Jupiter, Saturn, Neptune, Uranus. Whilst they are a long way away, they do exert an influence on the sun and the sun on them. So planets like Jupiter, which are much closer in, pull the sun out of position, causing the sun to actually wobble about in space. Now, if we study the position of a distant star, if we've got a star that's a long, long way away, we can see that star wobbling. So the bigger the wobble, the bigger the planet that's in orbit. We might not be able to see that planet, but somebody just came in and jumped straight out again. Okay. Threw me a little bit. So if we can see a star wobble, we might not be able to see the planet in orbit around that star, but we will be able to see the wobble. And if we can see the wobble, we can make certain measurements that will give us a clue about the size of that star. So stars make planets make stars wobble. That's the first thing we notice, is that we're using an indirect technique where planets make stars wobble. Planets like Jupiter can make the sun wobble around quite a bit, but that wobble is small and difficult to measure, but it is present. Back when we started looking for exoplanets in earnest, we didn't really have that technology sorted. Now we have. We've got telescopes up in space that can measure the position of stars very, very accurately indeed. And this is turning out to be a really good way of measuring whether stars have planets. Okay, there are other ways. We don't actually have to see a planet in orbit around a star. We can listen to them using radio telescopes. Now, a radio telescope is very, very similar to an optical telescope, except it deals in radio waves. A radio telescope is exactly like your sky dish. It receives signals from a distant source. We pass them into a bunch of electronics and amplify the signals. Objects in the sky give off radio waves in the same way as they give off light waves. And it's those light radio waves that we can catch, listen to, and make a lot of deductions about the nature of that object. So, in this instance, one of the first objects we determined that it had got a planet in orbit around it was a type of star called a neutron star, or, more correctly, a non-quiet pulsar or a magnetar. They make a lot of noise out in space. How do they come about? Well, when a particularly big star reaches the end of its life, it explodes, often with a very, very big bang indeed. There have been a few such explosions in our nearby neighborhood in the past 1,000 years. William the Conqueror recorded one in about 1060 AD, which was judged to be very, very bad for King Harold and turned out to be true. Tycho Brahe, the well-known Danish astronomer, he spotted one. Lots and lots of supernovae have taken place not too far away from us within our own galaxy. They leave behind themselves little objects called pulsars, these little objects called pulsars. What's left behind after a star goes bang is a very small, very dense lump of matter called a neutron star, occasionally called degenerate matter, because the matter itself is degenerated into neutrons. Why a neutron star? Objects, atoms made of positrons and electrons, and when they get compressed in this huge explosion, the atoms are pushed very, very close. The component elements, the protons and the electrons within that atom are pushed very, very close together. They cancel each other out electrically so that you have an enormous mass that is very, very dense, that is electrically neutral. So you might think, well, what's the use of that? Now, neutron means electrically neutral. Okay, so it's cancelled out all of its charge. But that doesn't mean the end of its life. Remember that original star was spinning in exactly the same way that the sun spins on its axis, Earth spins on its axis. You have to do something with that rotational energy. It's called the conservation of angular momentum, and exactly the same way that an ice skater spins up and slows down, stars do exactly the same. That original rotational energy has to go somewhere, so neutron stars spin very, very quickly indeed. Now, equally, that spin energy has to be conserved, so does an awful lot of that magnetic energy. So neutron stars are just very, very large magnets with a north pole and a south pole, and material that is pulled into the poles of those magnets because they're attracted, they fall in, they get compressed, they spit radio waves out into space, which we hear on Earth. We hear them as little clicks, very faint clicks. We hear them because their neutron star is spinning, and every time that great big aerial, so to speak, passes the Earth, we hear a click. And we hear them as a series of clicks. And because the neutron star is spinning very quickly, sometimes we hear them as a pitched tone, sometimes we just hear them as a dump, 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 out in space. Dump, 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 dump. And these pulses form a very precise, very regular series. Now, the first person to hear these pulses in space was Nikola Tesla, back in about the 1900s. And Tesla was utterly convinced. He had a very, very sensitive radio receiver. He was clearly able to hear these distant signals from different sources, and he was utterly convinced that he was listening to communications between intelligent species out there in the cosmos, and they were trying to speak to us. Tesla spent a lot of time trying to build some kind of device that would communicate with alien creatures, and that's largely what drove a lot of his bigger experiments. Some of these big lightning bolts was an attempt to turn the Earth into a giant radio transmitter. Unfortunately, Tesla's knowledge of physics, contrary to popular belief, Tesla's knowledge of physics wasn't that good. He had major trouble believing in Einstein's theory of relativity, largely because he didn't understand the mathematics, but he also didn't believe in, say, the inverse square law, which is a core of modern physics. Hard to believe, but true. So Tesla was utterly convinced that we were talking to or listening to aliens trying to contact us. Now, if we listen to an ambulance or a police car approaching to it, as it gets closer to us, we hear its siren going, the pitch of that siren gets higher as the police car drives towards you, and as the police car moves away, very common around Houghton Le Spring at the moment, since the natives are a bit restless, the pitch gets lower, same with ambulances. Now, the same is also true with pulsars. If we study the pitch of a pulsar, sometimes we find pulsars, they're not perfectly even spaced. Sometimes this pulsar speeds up and slows down in space. So the pulsar pulses get closer together. And then we know that this neutron star at the core is coming towards us. It's moving in its orbit. And then, hang on a minute, these pulses slow down again. And it's this rocking back and forward that gives us a clue that this neutron star might actually have a planet right next door to it. Somehow a planet has escaped the massive conflagration that came out of that supernova. It has survived and is still there, or maybe it was captured from another system, but there is still a planet there. And it is pulling that neutron star out of position. What's more, is we end up with one extreme, gives us one extreme, one bunch of pulses bunching up together, tells us where one extreme of the pulsar's orbit might be, and the other gives us the next extreme and back again. And this cycle repeats over and over again. So the variations in the number of pulses, the gap between the pulses changes ever so slightly, but it's consistently changing. And that tells us that we might have a planet around that distant pulsar. The gap in terms of time between the bunching up of pulses tells us how long the exoplanet takes to orbit that star. So we've used an indirect method not only to detect that exoplanet, but also to figure out how long its orbit is. And if we know its orbit, and if we have a rough idea of the mass of that neutron star, which we can get from other observations from theory, we might be able to work out how massive that planet is. And indeed, this technique worked. The first ever exoplanet was discovered in 1990, a long time ago now, 30 years ago. I remember the discovery, the announcement, as if it was, well, 30 years ago. They'd been studying the so-called millisecond pulsar in the constellation Virgo using a big radio telescope at Arecibo, and they detected this strange pulling and toing and froing of the pulses from this radio source. Came to the conclusion that it had to be an exoplanet. So we have indirectly determined the position of an exoplanet. We know that exoplanets exist. That's great. And this star in Virgo was an enormous distance away. So we found something. We found something out in space. We've confirmed that there are indeed planets around distant stars. We used to think that planets around distant stars were incredibly rare. I'm letting the cat out of the bag now, but we now know that planets around distant stars are incredibly common. They're not rare at all. In fact, they are the norm rather than the exception. What's more, further studies of the orbit of the motion of this little pulsar confirmed that it wasn't just one exoplanet, there were in fact three, one of which was nicknamed Poltergeist, because they weren't sure where it was. Amazing little object. So we've not one, but three exoplanets around a distant source. But a pulsar is not a good place to find life. Simply not giving off any heat energy, probably giving off a lot of radiation would make it uncomfortable and impossible for life to be sustained. We need to look elsewhere if we're looking for ET. The search for exoplanets was pushed further and further by this guy called Otto Struve, German-American astronomer if memory serves. In 1952, he suggested looking at a technique called Doppler spectroscopy or radial velocity shifts. It sounds complicated, and it is. Now, I'm just wondering if people are going to yawn and start going away, but it works like this. Good our old friend Isaac Newton, here depicted in the bottom left, he made a discovery, very, very important discovery. The ancient astronomers knew that they could decompose white light into its component, the same way as you have a rainbow. You could decompose white light into red, orange, yellow, green, blue, indigo, violet. That was well known. But, and this is why Newton is remembered on the old pound note, those of us who are old enough can remember pound notes. Newton called this experiment the experimentum cruxus. Very, very important. Yes, we cracked this joke before, so don't yawn. Wouldn't that make a good album cover? Okay. White light is broken down into its constituent colours, and then Newton recombined those colours by reversing the process to remake white light. So Newton figured out that white light was made up of lots of different colours, the same way a rainbow is made up, but he could put it all back together to convert the multicoloured rainbow back into white light. Very, very important discovery. There you go, there's that album cover. Never mind. These days we have refined Newton's technique to make a device called a prism spectroscope, and we use this device for studying the light from stars. Now, I'm not going to go into how it works, just accept that it's useful for breaking starlight down into its component colours. In the same way that if you remember old sodium lamps when the sky used to be yellow at night, they're now largely extinct. They've been replaced by LEDs. Sodium lamps are seen as old hat, old-fashioned, but they give off that characteristic yellow glow because that's what the element sodium does when you heat it up. When you warm it up with an electric discharge, it gives off this distinct yellow glow. When you look at it with a prism spectroscope, you see this characteristic pattern of lights. If you see that characteristic pattern of lights, stripes, bars and stripes, within the spectrum of a star, you know that that star, no matter how far away it is, contains sodium. What's more is that these lines exist at very, very precise wavelengths. So we can accurately measure how much of a particular type of sodium is in that star. So if that star is 100 light years away from us, or 5 light years, or even down the road 8 minutes. The same with neon. If you look at neon, you see exactly a different set of pattern at different lights, but we can see that the element neon might be in that star's atmosphere. So Struve's idea was that you look at the composition using a spectroscope of a stationary star. He then noticed that if you look at it with a moving star, those lines shift a little bit. This is the origin of the term redshift that you might have heard bandied around in the press. And Struve reckoned that those lines there, that they move, the shift alludes to how fast the star is moving. That's very obvious. Bigger the motion, bigger the movement, bigger the shift, the faster the star is moving. But Struve also said that the absorption line shifted towards the red end of the spectrum, the object is receding from the observer. If the absorption lines are shifted towards the blue end, then the object is approaching us. What then happens if you see those lines shifting back and forth? Clearly the star is moving. It is being pulled out of position by something around it. So Struve said that if you see these lines and you can record them moving over a period of days, weeks, or years, and they do so in a cyclical fashion, then there's a good chance that there is a planet in orbit around that star. And the size of that swing alludes to how fast the planet is moving. So we've got another technique for finding planets around distant stars. And it turns out to be a very, very useful technique for finding planets around distant stars. One of the first exoplanets to be discovered was around a star called 51 Pegasi, the constellation Pegasus. It was a so-called hot Jupiter. Hot Jupiter means that it's about the size of the planet Jupiter, but it orbits the host star very, very close in, sometimes inside, say, the orbit of Mercury. So this thing is moving very, very close. It begs the question, how does this planet survive if it is so close to the host star? We still don't have lots of good answers for that. 51 Pegasi, the planet around that was initially called Bellerophon, has since been renamed Dimidium, which I think is not a good name, but I like Bellerophon. I like it. It has a hint of antiquity about it. But it's not the only technique that we can use to determine whether stars are present. We can use the so-called transit method. If we study the light from a distant star, we can see that star and we can we suspect that there is a planet in orbit around that star. We might just see the light from that star dip as that planet passes in front. Now I've included this transit, an image of a forward transit, just to see if anybody is still awake, because I appreciate that it's late at night. You might be drifting off, but here's an image of a forward transit to wake you up. That certainly brought me up. I'd forgotten that was there. So if we study the amount of light coming away from that star and a planet passes in front of it, we might not be able to see that planet because it is so small with respect to the host star. But if we monitor the amount of light coming from that star, we see the amount of light dip. And as the planet exits the other side, the light recovers. Now, this is exactly what the Kepler Space Telescope was designed to do. Kepler Space Telescope was sent up into space about 10 years ago. And the idea was that it had a great big mirror, great big CCD cameras, exactly like the cameras that you've got in your phone, but only a bit more sophisticated, actually a lot more sensitive than when you've got in your phone. Send it up into space with some really, really fancy, these guys are all not working under corona, face masks on and stuff like that. They're just trying to protect the mirror from being breathed on. And Kepler was sent to look at one tiny area of the sky in the Milky Way. And throughout most of its active life, it spent its time just looking at that particular area of the sky. There's no atmosphere in the way. There's nothing else to impede it. So it just focused on this one particular area of the sky, and it made some astonishing discoveries. A legion of different planets, 4,000 odd planets around distant stars, just in that one small section of the sky. We very rapidly changed our opinion that stars with planets are not rare, they are commonplace. Kepler picked up thousands of different stars. We're still going through the data that Kepler was able to download and send to us. We still haven't anywhere close to reaching the end of that data, and still we keep finding information. Astronomers discover multiple planet systems from the Kepler telescope. NASA finds a dead star vaporizing a mini planet. All of the parameters that show that this planet is being ablated by this huge star. Strange goings on out in space. And then, of course, we find a solar system that is not massively different from our own. It has 8 principal stars, with the rocky planets close in, the gas giants further out. What's more, some of these rocky planets are in the Goldilocks zone, that particular area of that star's solar system, which are extremely conducive to the formation of life, how life on Earth evolved. So we've discovered that stars with planets are commonplace, and that planets around those stars in exactly the right place are also commonplace as well. So there's a good chance that we're not alone. We even went as far as to find a good candidate for Mr. Spock's home planet, Vulcan, from Star Trek, the series. Yes, Epsilon Eridani has got a planet in orbit around it. It's not particularly well placed, and the International Astronomical Union resisted all efforts from the Star Trek community to christen it Vulcan. Boo for them. Not fair. But it also turned up some really interesting, strange structures. There's an object. It's got a snappy name, KIC 846-2852, also known as Tabby star, after the name Tabitha, the astronomer, the lead astronomer. She discovered it. They saw some unusual light patterns coming from it. It was like the transit method, but not like the transit method. It would fade out and then come back, sometimes very quickly, sometimes very slowly. And the conclusion was that there was something around that star that was unusual. Not a planet, something big. And of course, the newspapers went absolutely potty. The newspapers insisted, the Daily Express, that this star is dimming because there's an alien megastructure surrounding it, says lead astronomer. No, quoting it horrendously out of context. They weren't sure what they were looking at, but of course the newspapers jumped upon it. And an artist's impression sprang up all over the interweb saying this is what must be in orbit around Tabby's star. Oh my, wouldn't that be good if we could find that sort of thing out in space? But no, this is pure conjecture, pure fantasy. When we point the radio telescopes at Tabby's star, we listen for signs of life, we find nothing. Absolutely nothing. There's no alien megastructure, no little green men waving at us and saying, please come in, the water's gorgeous. No sign of life at all. The most likely explanation for Tabby's star is that there is an uneven dust ring around the star. For some reason, we have a very evenly dispersed ring called the asteroid belt and another one further out, the Kuiper belt, around our solar system. And it is, as far as we can tell, very evenly spaced. But Tabby's star seems to have this uneven dust ring around the star. So it's not an alien megastructure. 2018, Kepler retired the Space Telescope. It had developed a number of serious technical problems. It had run out of fuel, time to let go, time to give up on it. They let it retire. So it's still out in space. It will be there until kingdom come. It's in a particular place in space where it won't fall into the Earth's atmosphere. It's a long way away from us. One day somebody might go out there and rescue it and bring it back to Earth just to put it in a museum, but I can't see that happening in the short term. There are lots of other up-to-date techniques for hunting exoplanets. We'll touch on a few of them. Astrometry, we've got a space satellite out there called Gaia that is measuring the position of these stars very accurately. It's a super enhanced version of the Bradley's technique, stellar parallax, being able to look at these stars and measure the tiny little wobble in real time. And it too is divvying up really, really good results about the number of planets around distant stars. We're using another technique called the occlusion technique, where we block out the light from a distant star, we get rid of all of that star, and it's giving us a good clue. A vortex spectrometer is one of the names for it, of what is going on. Here is a photograph of a real star called Fomalhaut. It's visible in the south, far south. We can mask out the light from that star, and we can start to see objects in orbit around that particular star. There's a little object there towards the bottom right called Fomalhaut B. We've been studying that object for some considerable time. We think that since we first photographed it about 2004, that has been subject to an enormous impact. We can see the thing fading over the past 16 years. It has dissolved into a bigger structure, a more diffuse structure. So we think this little protoplanet that was has now fallen to bits. It's failed. We can use this thing called a vortex coronagraph to get rid of the light from that central star, bring it out of the image, and we can directly see planets around distant stars. When I was at university, my tutor, Dr. Gerard McCartan, said, we will never have the technology to do this. Sorry, Gerard, but you were wrong. We've got it in abundance now. Okay, so we can start to see more of this. So here we are. I'll skip past that. We're rapidly improving our techniques for looking at signals coming from distant stars. We're improving the technology all the time of being able to differentiate signals from a distant star and differentiate from, say, the background noise, because space is a very noisy process. Here's the Arecibo radio telescope. The Chinese have got an absolutely enormous radio telescope that they're putting to similar work trying to find distant signals. We also launched in 2018 the Transiting Exoplanet Survey satellite, designed specifically, it's the follow-up to Kepler, designed specifically to look for planets around distant stars. Not long ago, it found its first exoplanet. CERT-2 is producing good information, and it is still running and will be running for some considerable time yet, giving us a really accurate view of how many planets there are out there in our part of the universe. We've also gone and found exomoons, moons in orbit around distant planets that are in orbit around distant stars. That's a real achievement. If we look at the information that's come from the Kepler Space Telescope, we come to some astonishing facts. This is reducing all of the data that we have so far, and bear in mind that there's a lot more data to come. We estimate that there are as many as 40 billion rocky Earth-sized exoplanets within our own Milky Way. 40 billion. And of that 40 billion, around 11 billion planets are in habitable zones around sun-like stars. So that draws us to the conclusion. It comes us to the conclusion, hang on a minute, with so many planets around so many stars, all in the right place with the right conditions to generate life, the sky is silent. Why don't we see any signals from space? Thus far, in the 40 years that we've been listening for life out there in the cosmos, we have found nothing. We've tried saying hello when we sent Pioneer 10 out to the outer limits of the solar system. We had a little plaque and some recordings on it that would say, howdy, we're here. We've tried beaming messages into space off the Arecibo reflector that give us a clue that anybody receiving this might be able to decipher this message and turn it into a message that some way of communicating with us. And we've tried listening. We've listened attentively, and we hear nothing. Still nothing. Have we been contacted? Have we missed something? The well-known WOW event, very well publicized, took place 1977. An astronomer called Dr. Jerry Ehrman was listening at this Big Ears Radio Observatory, Ohio State University, came back into work the following morning, and there was a printout. This message had been produced by the computers. It's an analysis of signal strength. The characteristics of this message, 6E0 UJS, 6EQUJ5, sorry, I misread that, has all of the characteristics of a carrier wave without a signal. And that's equivalent to tuning a radio into your favorite radio station, and the station stopped broadcasting. You will hear the background of the station there, but you won't hear any music. And that's a puzzle. What could have generated that nearly 40 odd years ago, over 40 years ago? And yet we've never seen a signal before that, like that, before then or since then. There's a theory going around that this transmission may have been, you can see where Dr. Ehrman wrote in the corner. He wrote on the piece of printout, it said, wow. So 6EQUJ5 is occasionally known as the WOW event. There was a theory that went around that this was actually caused by a pair of comets that were buzzing past each other. And those comets were supposed to buzz past each other again a couple of years back, and it didn't hold up to scrutiny. So we still don't have a good, solid explanation for where this WOW event came from. It's in a well-known part of the Sagittarius, part of Galaxy Sagittarius constellation, if that's what your birth sign is. That's where the signal came from. And it's a puzzle. Thus far, 2020, there is no evidence of any kind that there is life on other worlds. Why haven't we found ET? It's a major puzzle. There are a couple of explanations. There's an equation that how many ETs should there be? How many ETs should we actually encounter? The well-known Drake equation looks complicated. Yes, it is. But if we use the values that we've got from astrophysics and we plug those into the equation, we just run through the numbers. With the values that we now know, when Drake put this equation together, he didn't have good values for those equations, for this equation, but we've spent the last 50 years plugging values in and trying to come up with better estimates. And we use the rare Earth scenario. The Earth is rare out there in the cosmos. The number of intelligent civilizations that we might encounter, 4 times 10 to the 12th, is in a very, very small number indeed. If you're not into mathematics, if you don't understand that notation, just understand that it's a very, very small number indeed. It means that life out there is almost undetectable. However, if we're a bit more optimistic, if we plug in more realistic values perhaps and stop being quite so pessimistic, we come up with another number, 14 times 10 to the 6th. That is 14 million possible alien worlds out there, alien civilizations out there that are detectable. So we're looking at one extreme, we've got a very small number, and on the other extreme, a very large number of alien civilizations out there. And again, we haven't come across any. So why haven't we found ET? And this leads us down another path, which is perhaps the subject of an entirely new lecture in itself, the so-called Fermi paradox. Enrico Fermi, the great physicist, who gave us largely gave us nuclear power, a chance off-the-cuff remark. He said, well, if we're going to see so many alien species, if we're going to see so many alien civilizations out there, where are they? And it became known as the Fermi paradox. We predict there's lots of aliens out there, but we see none of them, also known as the Great Silence. Some of the theories that go that, well, we haven't contacted ET is we haven't evolved the technology to detect ET. Civilizations destroy themselves before they achieve spaceflight. Civilizations are destroyed by natural event before they achieve spaceflight. Some of the wilder, wackier ideas are that we live in a huge computer simulation. You might have heard that one buzzing around. Or we live in a zoo. We are quarantined from the rest of the civilized universe because we are barbarians, and so on. The Fermi paradox is great books written about the number of possibilities. Will we ever find ET? The clue comes in looking for biosignatures and technosignatures. Biosignatures, and this is the debate that I talked about at the start of this project, this debate that went on very, very recently. The theory goes that we will see biosignatures in the form of chemicals given out on the interior of an icy moon, Jupiter, Europa on Jupiter, Enceladus around Saturn. Biosignatures on the surface of Mars. Curiosity has already discovered the basic building blocks for life on Mars, but we haven't found life yet. We might find biosignatures on an exoplanet or the moon of an exoplanet, bioforming in a planet's atmospheres. We might not even recognize that particular form of life as a living organism. We might find technological signatures. We're probably not going to find transmissions we've been looking, but we might find some kind of artifact that they've left behind. One theory is that we need to develop so-called faster-than-light signaling, which we believe at the moment to be fundamentally impossible, but there are holes in the mathematics that say it is possible. We just can't do it yet. One theory is that communications between advanced civilizations are deliberately disguised to stop us eavesdropping. And without the smarts, without the intelligence, we can't understand them. And the idea that is used for that is say that, well, if you listen to noise on a line, I will come back to that, it's another, it's too complicated. Seth Shostak, one of the founders of the SETI organization, says that thinks that we are not far away, maybe 20 years away, from finding large-scale structures out there in space, although I've had real trouble finding any data, any evidence to back up that claim. It seems rather fanciful to me, but Shostak insists that we will find the equivalent of the pyramids of Egypt floating out there in space. I think that's far-fetched, but wait and see. Still, no evidence of any kind of life on other worlds, which is a shame, and yet we keep looking. We're asking questions, maybe we've already been contacted. In the summer of 2017, Oumuamua was an object. It was detected after it had fallen into our solar system. It stayed briefly and then flew off. It came, if we analyzed its orbit, it came from another star. We can be sure that this object did not originate in our solar system. It came from elsewhere in the Milky Way. A few astronomers have dared to suggest that this was in fact an alien probe. It was long and it was cigar-shaped, and its trajectory was unlike anything we've ever seen. For instance, it seemed to speed up as it left our solar system. And asteroids, Naturally occurring asteroids don't do that. They don't do that. So why did it suddenly speed up? We don't know. Maybe there's evidence for ET and it's been here along. We just didn't know what to look for. If you look behind a closed door, or a door marked "this door to be kept closed" at the Carnegie Observatory, if you dig through their enormous photographic archive, you come across some slides, photographs of the night sky that were taken way back in 1917, over 100 years ago. And there are signatures, little spectrographs that were taken all those years ago. And within them, carefully embedded within the data, is evidence of chemicals in orbit around the star that could only have come from an exoplanet. So the data was sitting there in front of us for over 100 years, and we didn't know it was there. So maybe we have to go looking through that data, looking through those archives for more information. So to conclude then, blimey, I've almost got this done on time. We found stars, distant stars with planets in the right orbit. We found planets that are capable of hosting life and that have water in the hospitable zone around that planet. We found the basic building blocks of life on Mars. And that leads us to come to the conclusion that perhaps life might actually be out there. We found that evidence. Maybe the evidence of ET's been here all along and we haven't noticed it. Maybe they've already tried to contact us and we missed it. We dropped the ball. We didn't get the full communication. But then again, there's a rather sobering thought. We are alone after all. Maybe we are alone. Maybe we are the vanguard. Maybe they are the ones, the pioneers out at the front. How does that make you feel? How does that make you feel that you are alone? Don't you think we should be a bit more responsible in looking after the planet and making sure that the loonies and the despots amongst us don't go and blow us all up? And that, my friends, is the end. If you've got any questions, now is the time to ask them. And I managed to bring that in under 50 minutes. So I have achieved my goal. I had to talk rather quickly at the end, though. So, any questions? Fire away.
Just a thought, David.
So there, hear me? Hello there. Say that again.
Just a quick one. If aliens had been here, would the respective governments, scientists, etc., hide the fact that there's been, i.e., Roswell, in the 50s?
Yeah, I think perhaps, given the state of the world back in the 1940s and the 50s, yes, if Roswell did happen, there's many believe that it did. Others believe that it was merely the American government testing secret aeroplanes that they'd stolen from the Nazis. If Roswell did happen, and it seems like something happened, we know something happened, would they keep it secret? Almost certainly back then, the climate would have said yes, they would. They would have sought every possible advantage to, the Americans certainly would have tried everything they possibly could to keep that technology to themselves. There's a book called UFOs from Behind the Iron Curtain that recounts that the Soviets had exactly their own Roswell. They were just much, much better at keeping it quiet than the Americans were. UFO crashed in some harbor out in, I think it was Romania, and they recovered a body. That body has never been shown publicly in perhaps, well, and it was seen, this event was seen by many, many people. This body was pulled out of the sea and witnessed by many, many people. Maybe it was a top secret Russian aircraft. They don't want to keep, they want to keep secret. But I think in the circumstances back then, they would almost certainly keep it quiet. These days, if the same thing happened with so many people watching the sky, so many amateur astronomers out there, so much in the way of internet chatter, I think they would find it very, very, very difficult indeed to keep it quiet. Such is the climate these days, that people are far more attuned and we have far, far better communications tools for distributing that kind of information around the earth very, very quickly indeed. I think back then they kept it quiet if there was anything. These days they would find it almost impossible to keep quiet. Or they would make up some fake news story about it being a fake story.
Yeah.
Something like that.
Just one other thing. If we look back to the planet Earth, 250, 260 million years ago, for 160 million years, the planet was occupied by dinosaurs, for want of a better word.
Yeah.
And let's just say the aliens came down in that period of time, had a quick look and thought, nah, and go back.
Yeah, exactly. Yeah, they could have visited at some point in time in the
Period
past.
of
And
time within the planet Earth.
yeah,
And we're still going through different phases of time. And I don't know. I think we're a special planet, and I think we're one off, quite honest.
why? Why do you think that?
I think everything just aligned at the same time to create the planet Earth. Having said that, if there's parallel universes, therefore there's going to be another Earth and therefore life. Perhaps.
I completely agree. You look at the complexity of life. I got beeped there. I got beeped by a little message in my ear. If you look at the complexity of life, you could argue and say, hold on a second, life is incredibly complex and has come about through a variety of strange and interesting processes. But there are a bunch of astronomers, many at that NASA conference, the one that I talked, that said that life is an obvious and essential consequence of the thermodynamic principle, that atoms have an inherent, I wouldn't say ability, an inherent tendency is a better word, to organize themselves. They organize themselves into compounds, they organize themselves into molecules, and from there into bigger structures. So the direct consequence of the nature of atoms is that they organize themselves, because that's what atoms do. And they've seen this happening. It's building it into part of the theory of thermodynamics. And it's more than just a conjecture. It seems to be an idea that is gaining momentum, that life may be an essential consequence of an environment that is in the slightest bit conducive. Obviously, if you've got volcanoes going off, that's not going to be a good place to set up life. But where we thought life was utterly impossible, like black smoke is on the bottom of the sea, we find life is in its abundance. We find life growing in the most impossible of circumstances, like beneath the ice in the Antarctica. Other regions where we thought life was utterly impossible does seem to survive. Now, Alan's just mentioned, there was through chat, that there's a form of life that has been discovered, form of bacteria, if I'm right, that seems to, or there's a search for alien life, there's a possibility that certain forms of alien life could breathe hydrogen. And since an awful lot of the gas giants are composed largely of hydrogen, there's a possibility of looking in the outer atmospheres of planets like Jupiter and Saturn for animals that might be able to survive there in some form. So we might be looking for life, but it might not look like you or I. And some might say, that's a good thing. Personally, me, I'm a gorgeous golden-haired Adonis, but, you might be different. That's me being silly. Anyway, good question, Ian. Thank you. Anyone else? Anyone else? Come on, Mr. Catty, you always have something good to say. Is he still awake?
All right.
There we are. Hey, Rob. You've gone dark, Rob. Put a light on.
Now, it occurs to me that, in fact, it's the transmission of light, information, etc., takes so long that it may well be that at this present time, things have occurred in other planets, other universes, it's a kind of universe which are so far away that in fact we have no knowledge of them.
A very, very good point.
It is almost certain that there is some sort of life in other worlds, in other galaxies, in other kind of, or if you in this galaxy. The question is, how has it developed into the sort of sentient beings that we are? And it won't necessarily develop along the same pathway as life has developed in this world.
We have no guarantees of that. I see exactly what you're getting at. If you think about the nearest galaxy to us, which is the Andromeda galaxy, they are 2 million light years away from us. So what could have happened differently over an Andromeda? You know, there's a hell of a time difference between us. If the two galaxies were born at roughly the same sort of time because they are the same local group, same part of the same family, then it's logical to assume that you might have planets, a number of planets where life started to evolve at about the same time, but we're unable to communicate with them because they're either 2 million light years ahead of us, 2 million light years behind. But the distance is this gap in time, which is at the moment insurmountable. Only Captain Kirk can travel faster. Well, not only Captain Kirk, but lots of other space science fiction films seem to be able to travel much faster than the speed of light. It's the only way you can get from A to B without, having to use generational ships, so-called. But yes, it's an interesting question. Maybe it's just simply the gap between us is insurmountable. But remember, there are a number of physicists who are utterly, utterly convinced that Einstein's limit of objects moving at the speed of light, believe that that can be circumvented. There's enough holes in the mathematics that say that, well, certainly perhaps a massive object couldn't move faster than the speed of light. There's no way to do that. But information might be able to. And there's, of course, this Alcubierre principle for making a spaceship move faster than the speed of light. It's still theoretical, but we've improved the theory since the idea was first proposed. So who knows? Who knows what the limitations are? We may still be, who knows? It's an interesting idea. To the best of my knowledge, Alan, the Black Sea Angel is about 6 to 7 inches long. That's the only information I have.
Okay.
There we go.
Well,
Anybody else got some more questions? Rob, go ahead. I'm sorry, I cut you off.